Hey, no, how are you? Sorry, I had thought that I posted the lab. I just did that right now, so you should see it on Canvas. If you want to download that. I probably have done that in a different course room. Let me double check. Okay, we'll go ahead and get started. I think if the people can join us, they'll be able to join us. So if you wanted to take a look at the lab, in this lab, you only need to use your IDE. You can use idle, or if you want to use Linux system, you can. You don't have to, as it would work with your regular IDE. Okay. Let me delete something real quick from, I had posted in the wrong course here. So, all right, I'm going to go ahead and go into screen share. Okay, good. I'm glad you're doing good. Okay, so in this lab, we are going to look at how to optimize Python algorithm. In the chapter, it talks about looking at, your runtime, looking at your time complexity, and be able to rewrite the program multiple ways to really evaluate which approach will be best. And at the end of the chapter, it goes over caching and using memory allocation to be able to improve your Python application performance. Now, whether you write this, you write Python application for system or for web application, or even for server connection, we can look into how we would use memoization. So in this week, we are going to mostly apply the knowledge from last week, which we used timeit. But instead of using it in Linux, I want to show you that you can implement that in your IDE. And there will be an exercise that we would use func tools. So there will be modules that we would implement, which are libraries, and we would be able to tap into how to use decorator and memoization. Okay. So to start, we would start with the definition for memoization. As you recall from the chapter, this really tapped into using the temporary storage, which is cache. And we would use this to be able to optimize how we design and develop our algorithm for our software. And a cache is a storage location, and likely that it will be inside the processor. In some cases, we can actually cache it to a certain location of our system on RAM. But depending on how the architecture of your processor is designed, but most of the time we would see that cache being used with the processor. So memoization allows you to implement caching with the Python function. And there are a couple of ways that we can do this. And so when you use this with the function, you have to take a look at its parameters, what you pass inside the parentheses, right? You pass inside the function. So if the function is memoized, what it does is it takes that function output and store it in a location and then use it to be able to execute or use it in another function. And we would take a look at that. So if you look at something that is recursive, that means a function that calls a function to be able to compute the output, we can think about how we would use cache to be able to quickly produce the output for our application. So the way that we would design algorithm for memoization would have a couple of steps. First, you need to define the location of where your data is cached. So with that, you have to specify in Python the directory or the location where it would store your function information or the results. So whatever the function returns, that's where it's going to put the data. Second, every time that that function is called, it's going to take the stored information from the cache and it's going to compute it in the call. So with that, if you understand compiler and how the system handle this, so when we think about that, right, the stack would then have the return information and necessary information from the function, like variable and what it needs to execute in order to produce the output. So if you keep calling that function, it's going to go back to the cache location and it's going to retrieve the result and it's going to use that result for the next call. And we don't want to rewrite the data all the time. So what we need to do is we just need to store it and then go and have it retrieved for every single use afterwards. Okay. So in memoization, we would approach it using two components. The first component is to use a decorator in Python. And we talked a little bit about this, about using the @ symbol. But a decorator in Python simply means that you're able to modify the behavior of your function. So without changing the function itself. So we might be able to have it execute tasks that is slightly different than how it was originally defined and be able to save that information and keep repeating the process over and over again. So that means that the decorator would take the function, we can add some additional functionality to it, and then return from it. So that way that we can use that data for the later call. So that's how you would use a decorator. Simply that it just allows us to change the behavior of the original function. And you can have a function that is decorated, right, to be able to call the next function. So with that, the task changes. The second component that you can implement with cache is called the LRU cache. This is part of your func tools. So let me edit this real quick. As I did not label this properly. So in the func tools library module, you would see that it has a specific or different type of functions that work with cache. And so we want to focus on LRU cache this particular week. And so this allows us to reduce the execution time as it stores that information about the function. And normally you would see that the func tools itself with the function, it is a decorator in Python. So ultimately we are using decorator, but using a library, you would use specific function. So let's go take a look at the documentation before we start. So here you would see cache. And if you compute something like factorial would normally be applied with recursion. So basically a factorial is you would take, right, all the prior numbers and be able to multiply. or if you do like Fibonacci, which is what we're doing, so all the prior numbers. So anything that would be recursive, we can think about how we would implement cache. Because in recursion, if you don't allow storage, what will happen is it's going to eventually lose the data as it computes out in the later steps, because it's not able to retrieve fast enough. And as it is temporary, you won't be able to have the data. It would just point to the location where the data would be. So that will be the challenge with the recursion when you're working with the larger data sets. So we should consider implementing cache-based function or libraries. So on here, you would see various class information and function that you can use. And the particular one that we're going to do today is going to be the LRU cache. And so it is a decorator, and it allows us to wrap the function. So that way, when we call it, it would simply go to the temporary location to be able to do that. And the cool thing about this is you can control your storage by setting the max size. So we can specify the amount of storage that we want to use to be able to store that data. Because when you're doing recursion or when you're doing synchronous programs, simply going line by line, you would see that it takes up a lot of space, right? And what will happen is it's going to become expensive. So it's going to utilize a lot of the resource and the processing power to be able to execute that. So on a larger application, if something is repetitive, we should consider using something like a LRU cache. And so here it gives you a little bit more information. You can think about how you would implement things for dictionary, keyword arguments. Search algorithm is probably also efficient with this, because if you think about Fibonacci sometimes is implemented for search algorithm. It's implemented for a lot of different things. So here there's some example, and we would do a Fibonacci example. And so I would refer to the documentation if you want to implement this. Now on the networking and the security ends, if you're in that area, you should think about your network status, how it needs to be able to maintain the status. And so simply when we cache the information about our network status, so for example, contacting HTTP server or your web server, that will be useful in using cache. Okay. So when you look at the lab, a big chunk of it at the beginning simply explains to you what we're going to be using. And the syntax for LRU cache is noted here. Here, the max size you can specify. And then if you want a certain type, you can include that as it's provided in the documentation. So in all the exercise we're going to do today, and I try to design it using one concept, which is Fibonacci. And what we want to do is we want to design programs to solve or to generate Fibonacci sequence or a value in Fibonacci using different techniques in Python. And so you can see as you run timeit module, which one is going to be better. And so when you go into development, you have to write your algorithm multiple ways to really see which way is the most efficient in solving the problem. So Fibonacci sequence, if you're not familiar with it, this is addressed in CIS7 and other classes. It is a group of numbers that is built from adding the two prior numbers. So when we say a sequence, that means that it has a pattern. And so unlike the series, a sequence is just a group of numbers that will have some kind of pattern. So on a Fibonacci sequence, we would have seed values. So in a sequence, you always want to start with the beginning value. So our f of 0 and f of 1 is going to be 0 and 1. Those are your seed values. So that's your starting point, your seed. And we use Fibonacci in computer science or development to generate random numbers. You can use it for data compression, hash, search and sort. You can also see this in display for a computer system. And in nature, if you look at a pineapple that is representing Fibonacci sequence, or if you're looking at like cactuses, sunflower, daisies, so anything that spans from the core and it expands out, you would see that it is a form of Fibonacci. So for the Fibonacci, if we start with 0 and 1 at the beginning, we would take those two values and we add them together to get the next value, which is 1. So if I take 0 plus 1, I would have a 1. Then I move to the next one. So I would take a 1 plus a 1, I get a 2. A 1 plus a 2, I get a 3. So to generate the f of n, I simply take the two prior numbers and add them together. So for Fibonacci, as it can go infinitely, right? Like we can try to determine the 800th number, and we can simply program that for our system to be able to generate that number. Or you can have it print out every time that it generates a number in the sequence. So in this first program, we are going to do a costly or an expensive program. That means that it is a traditional program where it is synchronous, where we would just use variables and conditional statement to be able to find the 30th value for Fibonacci. Okay, so let me go open up the first one. Any questions so far? So here I'm using Tawny, and you can use idle or VS Code. There are times that you will need to install the appropriate module. So make sure that if you're using an IDE, you need to link it properly. If you want to use the Linux virtual machine or the terminal using Nano to write your program, that's totally fine too, right? As long as we have an editor and an interpreter to run, that will be good enough. And you need to have Python 3. So I want to be able to have timeit, and according to Python 3x, right, timeit is now included with their newest package. So if you install the Python, let's say 3.9, you should have timeit. If you don't, you can also do pip install, or you can go and find out how you can install by reading their documentation. Then after I import timeit, because I want to measure the time for my expensive Fibonacci program, I would start with the definition of my function. So import timeit at the top, and I would define my function called fib, and here in the parameter, I'm going to pass num. So that will be a variable that's going to store the value. So on the stack, if you think about this, it's going to push this every time the function is called num. And because Fibonacci is a sequence, so as you continue to do that, it's going to have to keep pushing and updating the variable. This is for our seed value. If your num, if the value is 0, it's going to be equal to 0. Recall that when you look at the document here, right, our seed values start with 0 and 1. Now, some Fibonacci sequence actually start at 1 and 1. It doesn't make a difference. But in the program, when we write that, we want to make sure that that condition is met. Okay, so if it is 0, it's going to return 0. That's our seed value. Elif, if it is 1, it's going to return 1. So these two things are going to be for our seed. From a function, and the purpose of a function is to return the value from it. So we want to return. And a function that calls itself is a recursive function. So this one is a recursive function because it is fib and it calls itself. So as it calls, it's going to have to retrieve the return value from the last call to build out the result for the next return. So here it calls itself. And because I'm using the 2 previous number, I'm going to take the num subtract 1 plus fib num subtract 2, right? Because we're taking 2 prior number and add them together. So num minus 1 and num minus 2 just represent f of n minus 1 plus f of n minus 2. And I want to time this, so I simply wanted to do a print, and I'm using timeit function or method. And for the time, what it's going to do is going to go and pull fib with the parameter, right, from the location. So we have to use a string for this. And then we want to state that the globals are going to be globals. And I only wanted to time it once, right? So in the chapters, this chapter and this last chapter, it talks about how you can run it 1,000 times, 20,000 times. So if you wanted to run it 1,000 times, you would. If you want to loop it 1,000 times, you would change that here. But I wanted to only execute 1 time, and then a second time and a third time. So I wanted to do 3, but not loop. I wanted to do it individually, so I can measure the worst, right, and the least time from the best. Okay. All right, so let's run this. And your system might produce a little bit different time as you have different processor compared to my system. Okay. So when we run this, as you can see here, right, I have a 0.51 milliseconds. I have a 0.46 for the second try, and I have a 0.45. So what I did was I'm looking for the 30th number in the Fibonacci sequence by calling this function, and it has to do it 30 times in order to get to the 30th number. Actually 28 times, because the first 2 are the seeds. So the slowest time I have as an output is a 0.51. Okay, that has the highest value, so that is the slowest. And the fastest is going to be 0.45. So in a regular recursive function call, as you can see, when we time this to produce Fibonacci 30th value, it's about 0.5 of a millisecond. So coming back to our lab document, I want you to put that program into your IDE, and I want you to run it so you can assess the time. Then you are going to take a screen capture of your code and your output. And I want you to write down the highest time value from that call, from the execution. So for me, this is the highest value. So that will be the slowest. The reason why we want to note this is we want to look at, out of the 3 tries, the worst case is going to be this, right? For the same program. And when we assess that with another algorithm, we want to assess it against another algorithm's worst case. So when we move into cache and using other approaches, we want to look at the amount of time that's going to take the most. Okay. So once you have your code ran, and take a screenshot, then put down the slowest time. We want to use this for comparison, so it's important to make note of that when you're trying to look at the analysis for your application performance in Python. Then in the next part, what we're going to do is we are going to look at how we can use module and its components to improve our program, and we're going to measure it. Okay, Any question for number 1? Now, there are many ways to write Fibonacci. I'm sure you probably find it all over the internet. And we're going to look at some of the primary approaches. It doesn't mean that those are specifically the ways. Everybody solve problems differently, right? In general, you're going to see something very similar to this in all languages. So you might see this in C++, very close to this. So recursive function is, it's commonly used in like Fibonacci sequence, Lucas sequence, factorial, and so on. Anytime that you deal with the prior numbers, recursion is often implemented. Now, a lot of the coding camp or when you go for jobs, sometimes they would ask you to solve problem with Fibonacci. So it's always good to be exposed to that. Okay. All right, any question on 1? Okay, so that's a very simple basic program to start. Then we're going to move into using func tools. And in number 2, we are going to implement cache. So in our algorithm, not too much. It's going to look very close to what you had in number 1. And I try to make it cohesive so that way you can see the difference when we add the cache. Now, in number 2, let me get that open on IDE. Let's clear this. So since we're using the func tool modules, you are going to have to import it in. Okay, if your IDE, if you're getting an error when you run this, right, likely that you don't have it installed on your IDE or linked to your IDE. Most IDE would have some kind of tools or management menu. So if you're using Tani, you are going to click here and you're going to go manage package. And then you simply type func tools. And once it's going to go and pull it from PyPy, and you simply click install. So if you want to know how to use VS Code, link your packages and your module, you can also go to Microsoft tutorial. They show you how to do that there. And also now, even if you install it on the command line using pip, it doesn't always link to your IDE. So I put that in the lab just to keep you reminded that when you're using a third-party package or module or tools, you need to make sure that your IDE sees it. Okay, so that's very important. So make sure that happens before we run the program. The second statement here is just like the first. We are going to time our program. So we are going to use timeit. So we're going to do an import timeit. And since we're using the function from func tools called LRU cache, we simply make sure that we are decorating here. So we use an @ symbol and then our module or library, and then our function. And in the parameter, you want to specify how big you want to store as cache. So here we're going to go 150 meg. Then after that, we would just follow it up with function definition. So we would have fib, just like the first one. And then in this one, we would use conditional statement, and it is a recursive function as it calls itself. And I'm still doing the same thing. I'm still looking for the 30th value in the sequence, and I want to be able to time it. So it would be just like number 1. And I wanted to check it, measure it 3 times. Any question regarding the code for 2? All right, so now we're gonna go ahead and run. So here you would see that it's gonna give you different units, right? I'm getting your E notations. And I'm gonna come back to 1 and I'm gonna rerun that so you can see the difference. Okay, so this is my number 2. This is my number 1. And if you want to check the difference, you can open up your scientific calculator. So I can take my calculator, right? And then make sure that I'm in scientific mode. You can simply copy the time, the slowest time, and then put it into the calculator for number 2 and subtract it from the slowest time for number 1, and you would see the difference. Okay, so it shows like negative, that means that 2 is just faster. So you can see the difference in time when we're implementing cache. So it is definitely faster as your decimal value changes here. Okay. And with that, we didn't modify too much in the program. Our function definition is still the same. It is a recursive function with the conditional statement, and the num as a variable. The only thing that we added from 1 to 2 was to use functool LRU cache function. And we dedicated a portion of the storage, our temporary storage, for the return value as it output that. And it repeatedly call it, so it just goes back to that location to pull the data. And that reduces, right, the execution and also the resources. So on stack. So what you would see is definitely an improvement in using cache. Any question? Okay, so we look at the difference using timeit measurement there. So as you complete the second exercise, which is not a huge modification from the first, take a screenshot of your script and output. Make note of the slowest time. And I want you to answer, in comparison to exercise 1 output, is there an improvement in the runtime? And it's pretty obvious, right? If we're looking at the decimal points. Okay. Then we want to make note of the answer. So for this number 2, screenshot slowest time and compare that to 1. Is it faster or slower? Now, from the first page, we recall that memoization isn't just using LRU cache function from functools. Another way that we can do this is to use a decorator. And a decorator, as it's defined on the first page, it is a way that we can modify the behavior of a function without changing its nature. So you don't have to redefine it in a different way. You can simply use it and modify it as it called. So we can use a decorator. Now, in this case, we're not using the decorator like how we would use with an @ symbol pointing to a specific storage location that represents a library or whatnot. But we are going to decorate a function to call another function so that way the output will be different than its original state. And when you're using the cache from number 2, it is a decorator. So both of these are implementing temporary storage either way. Okay, it's just different way to really write your code or solve the problem with different technique. And I'm going to show you where. So earlier, we saw that we established the cache with the size here. So what that does is it tells the system to reserve a portion, that size, right, for the return value. In the third program, we are going to define 2 functions. We're going to have the inner function and we're going to have an outer function. But from the outer function, we are going to create a container that's going to store our temporary values or our return values. And that's where it's going to go and retrieve. So it is still a way for us to utilize the storage to pull the data for our task, for our execution when our function is called. So in number 3, let's get that open. I have the first statement is timeit. Very similar to the other 2, but unlike the first 2, now I have 2 functions. One is going to decorate another. Okay, so when and the way that you approach this, you would see the algorithm step from the page 1. You are going to be able to first define your function. And for the parameter, we simply say that we are going to pass the function. We're going to set up a storage location container or the storage container here. In the inner function, we simply pass arg as arguments. If the value is not in cache, right, it's going to go and find the return value there from that function and then return cache. So this inner function allows us to modify the behavior of the outer function. And what that does is it's going to update the container as the outer function is producing, and it's going to go and retrieve the value. So you would still have the 30th value for Fibonacci. It's just a different approach in using one function to decorate another. And just like before, we would have 3 statements for print, timeit. So we are going to measure the time and output it on screen. And we're going to do it one by one. And so we can see the slowest time. So when I run this, I want to really look at how number 3 is really compared to number 2, because that will be the closest to how we would implement cache. They both implement cache, right? They both use decorator because func tools use decorator. But writing it this way with 2 functions, is it better than writing it with 1 function and using the module? So here's my number 3. So you can see that the time, right? That's what it would look like. And again, your system might look, the time might look a little different because we have different hardware. So what you want to do is you want to take the slowest time from number 3, and you want to compare that to the slowest time on number 2. Okay, so when you work on 3, just a few lines of code, not too much, put that into your IDE, run it, then take a screenshot to show that you did that. Then write down your slowest time. And then we want to compare that to the result from number 2. And we wanted to see if there's an improvement. And realistically, if you do this, right, you want to make sure that you go through the loops and test it. We would want to time it more, okay? But for the sake of the exercise, I want to show you how you can do it, and then you can expand on it for practice. So in the number 3, we also using cache compared to number 2. It's also using decorator to have cache. And in number 2, we were able to set the size. In this one, we simply use a container. Okay. All right. So after you have your result, you would compare and see which approach is better. Any question regarding 3? Now, if you're using Linux terminal, like what we did last week, or if you're using Mac OS terminal, make sure that you do pip install the func tools when you do number 2. And if you don't have timeit, make sure that timeit is seen by your system by installing it. Okay, so look at PyPy or their documentation. They show you how to install. If you have Python properly installed, installing packages is really simple. You can install pip or use pip, or you can use wheels or other type of tools to bring it in. Okay. Now, when you notice that when we do timeit, we just simply implement the function call as a string here, right? Because it needs to go and retrieve that from the timeit library. So if you want to know for sure, take a look at timeit methods. How it's documented, what's used, what's the parameter in it. And here we're only using 3 parameters. Timeit actually accepts more parameters. So you can specify strictly on how you want to output the time, like controlling the precision in the output, like the number of decimal you want for reporting purposes and so on. Now, you do see sometimes when we take a look at how this is used for, like, if you go into data science, you can think about like how it would be used to write an application to do data analysis. Sometimes that would correlate with machine learning and so on. So we'll get to an exercise that will touch a little bit more on that. Okay. Any question for 3 before we move on? All right. So some of you probably have seen this approach. I think I used this in C++ for my CIS7 class. And so, like I said before, there are many ways to really solve Fibonacci sequence in programming. A lot of times people revert to recursion, and you saw 2 other techniques using cache, right? And in this one, we are going to use dynamic programming. And simply that is implemented with recursion. What you can do is, just like the others, right? Software is about using data structure. It's about where you put your data and how fast you can retrieve your data for execution. So it's still going to be able to store your result, but what it does is going to set up location to store the subproblems for the subtask. And so that way it would be able to recompute when it calls itself, because it's recursion. So in this one, we are going to do an array or a list in Python. So what you can do is you can set up a container, right, on how you want to store the value. Okay. So in number 4, we are using dynamic programming. And like before, we are going to import in timeit as we are measuring time or runtime of our functions. We are, but unlike the others, in this one, we are going to set up a container, and that's going to contain our seed value for Fibonacci. We are starting at 0 and 1. Now, we want to say that if it is 0, we're going to return 0. You can also add if it is 1, return 1. But these two values are required to start Fibonacci sequence. And I want to go all the way to the end of the array. So as it builds, it's going to expand and generate that and return it to the array. So I'm going to store more values as I go along into the array. So if we're looking at the 30th value, right, it's simply going to put it into the array and be able to retrieve it for the 31st. And then, the 31st is used for the 32nd and so on. So that means that I have to use, so this is going to be less than the actual array size. Then we're going to return, right, the index n from the array. For the else statement, we are going to append, and again, it is a recursive function, so it's a function that calls itself, and you see that in the call here. Okay. And so it needs to pull the return value from the last call and plug it in. So it needs to go for the last 2 numbers values and then add them and then put it back into the array. So dynamic programming is about how you store as you execute the subprocess. You can use a variable, but in the case where if we have a sequence like this, it's better to implement a larger container, like a list, an array. You cannot use tuple because tuple don't change, so you cannot append to it. But in some cases, we might even consider using a dictionary. Okay. And again, we are going to find the 30th value on the sequence, and we are going to time 3 times. And that's why we had timeit at the top. So this was number 3, right? This was number 1. And I'm sorry, this was number 3. This was number 2, and this was number 1. Okay. And now I'm going to run number 4. And so as you can see, right, this is the time that it produced. It tells me that the runtime is this. Okay. So this is high. So when we compare this, is creating an array using dynamic programming better than using a decorator or setting up cache, right? And that's why we're doing the timeit. We wanted to see which approach would give us the most efficient program. Now, last year when I taught this class, because of the holiday, right, we didn't do too much in memoization. I did come back to it in a later chapter. So this year, this is specifically different than the last time I taught this class. So you guys are getting, a little bit of practice with this. And I think this is really useful for software engineering, for some of you that are looking to do that. Or even when you apply this to write stuff for network security, server administration, things like that. So, and if you do want to do other languages, if you understand like the approach in using cache or dynamic programming, it carries into C++, Java, and other languages. So, all right, just like Python modules, we do have access to specific modules. There are modules specifically called cache, and also like when we work with space optimization, there is space optimization library that you can use with Python. Okay, but we are not implementing that this week. Okay, so for 4, put that into your IDE, run it. But I want, when you type it in, you need to think about like what you're typing. What does the program mean? What is it doing at a certain line? After you run it and have the output, take a screenshot of your code and your output. Write down the slowest time for dynamic programming result. And I want you to compare it to the cache programs, the decorator and the LRU cache. Is dynamic programming faster or slower? And, we're not truly using scientific approach because we need to time it more in order to really compare. But I wanted to show you how you can write different ones and do the comparison initially. Okay. So is dynamic programming better than using decorator or caching? Using func tools. Okay. And we need to think about why, right? Why is it better or not? So in relation to what we talked about this week with the big O notations and our assessment of a program, we should think about how we would wait in space and time, right? In order to reduce time, you have to have storage. In order to decrease storage, you're going to have more time. So the program becomes slower if you reduce the memory storage or temp storage. So there is an inverse relationship with space and time. So you have to weigh the risk when you design application or when you write out your code, you have to build your algorithm. You have to think about, do I give it more space, creating containers for storage or set up cache, or do I just have it slower with less space? Okay. Any question? So that was 4 with dynamic programming. So now what we're going to do is we're going to see, and many of you probably have seen this. I think when I taught 17A or programming classes, I normally see examples in the textbook that they talk about space optimization, reassigning your variable and reusing that space to update the values. So it is still creating a container, right? But instead of storing more permanent values, it would gradually update the values and reusing that space. And so therefore they call it space optimization. Okay. This is very common in sorting, right? Like if you think about a bubble sort program, sorting, we got to move values around to be able to, like, it bubbles out. So when you do a bubble sort, you got to put things, values into container and then swap them. Okay. Because if it's lower, then you're going to move it to the left. If it is higher, you're going to move it to the right. But there's no magical space, right? You have to set up space to be able to swap the values. So we move it from one to the other location, or we can use a pointer, right? Things don't move around. It's just in the location. We just point it to the area of the memory that would have the value. Okay. So for 5, we are going to do a space optimization program. This one, we are going to, again, use timeit. So let me open this up. So it's a tiny bit longer, but not too long. Import timeit at the top. We are going to define a function. And we're going to pass n as a variable for that function. Then we are going to put in our seed values as variable A and variable B. And A and B will get updated as we move further into the sequence. So we would say that if it's n is 0, we would return 0, right? Or A, we can also say return A. And else if n is 1, we're going to return B, which is 1. Those are our seed values. So those condition needs to be set. Else, we are going to loop. So in space optimization, you often see that it is not using recursion, it is using iteration. So we would have a for loop for index in range, right? 1 to n. We are going to take the seed, we will start with those, add them to generate the next number, and then update them as we move the f of 0 to f of 1, from those two to f of 2 and 3. So we would update the A and B. So as we move further in the sequence, we need to update the value from the result of the sum here to the variable and return from it. Then we're going to execute the timing. And we are still looking for the 30th value in our sequence. Nothing has changed. But it's just our algorithm is implemented differently now. This one does not use recursion. It is using a loop, so it is using iteration. And we're using a variable reassignment throughout. And so this approach is for space optimization, so you'll be using that space. So once you have that program, you are going to go ahead and run. Then take a screen capture of your code and your output. Put down the slowest runtime. And we want to take this and we want to compare it to the cache program. And you can even compare it to, you can think about, is it faster or slower than dynamic programming, which is using an array? An array store things in order, right? That's exactly what we need for our sequence. But it does take up more space. So we can think about, oh, is a variable using 3 variables, is that better? Right? We talked about space and time. Is it better than the array? So for C, after you note the slowest time, you would then compare that to the cache and the decorator program and see if it is faster or slower. Okay, so take a look at your output. Find the slowest runtime or the highest value there, and then compare it to the highest value for 2 and 3. Any question regarding number 5? Sorry, I posted this a little late today. I had posted it, but I was really sleepy this morning when I posted it. So I added it to the wrong course. And then when I logged in and I was like, oh, what happened to lab 3? So I had to repost it on your course room. But this is not due until Sunday. So you do have a little bit of time to work on this. Or if you have any question, you can let me know. Okay. And this is a fairly easy lab, so. Okay, any question on 5? Okay, so we just got to do one more and then answer a couple overall general question and we'll be done. And I tried to target all the elements that covers in the lecture or your book, your text, because I feel like this is useful for, as you expand your skill with Python programming. And especially for intermediate and advanced, it's really important to know how to be able to apply these concepts when you write your script or your code and design your algorithm. Okay. So for the next part here, the text also talk about joblib, and particularly in joblib module, this is a library that contains various components, but there is a class called the memory class. And it does allow us to set up storage, but instead of in the temporary storage, we can actually put it on disk, like your hard drive or like C drive or, a location on our disk. And so that way we don't have to re-execute something over and over again, very similar to what we talked about with cache. But in this one, you are setting up storage on a permanent location instead. It also supports cache usage for recomputation. And you might see this again, or you might read about it. This is used in parallelization, and often you would see this being used with ML or machine learning. So when we say it's able to execute parallelization, that means that your processor is able to execute tasks at the same time using its core. So if you have 4 core, all 4 of your core can execute 4 tasks all together. Now, we don't just tap into the CPU. If you know machine learning, it uses also GPU. Okay. So you can implement this with processor and be able to maximize the capability of the multi-core processor to compute. But instead of recompute, we can execute more tasks if we are assigning or allocating storage properly. Okay. So here, these are some of the additional benefits. So no specific dependency, so you don't have to rely on other libraries in order to build that out or packages to add to it. So that's good. Save cost and time. So you are saving space, but also be able to improve efficiency with runtime. And it's easy to implement, as it would be easy to learn from the documentation. So keep in mind that when you are doing memoization, large objects, of course, use a lot of memory. And as we put that on storage, it is to the speed of your storage. So if you're using it with RAM, it is the speed of your RAM, okay? Even if your processor is benching, if it's clocking faster than the RAM, it is only able to read and write at RAM speed, okay? So it does have the functionality with the dump. And if you look at the example that they use in the documentation, the people who contributed to this project, they actually, work on like network. They provided network examples and also like security related examples. So, it's pretty interesting. So this, sorry, it corrected me on here. So autocorrect. So it should be memoized. It is suited for small input and output objects. Remember that we don't want to use these things for the larger objects because it's just taking up a lot of space, and accessing it might also cause some delay. So we should consider this for the smaller input and output objects. And when you build out the function, think about how it would, in some cases, like if you're looking at machine learning, it would require, right, more complex computation with the objects. So it noted a little bit of benefits and disadvantages of your module. Now, if you work directly with the OS, make sure that you use the installation method using pip, or you can refer to the documentation and learn how. But if you are using IDE like what I've done here, okay, I have Tawny. So again, I just need to make sure that I add the package. So I simply look for joblist and then click install. I only need to do it once. So it's going to pull that from PyPy. And if you're using a different IDE, you just got to make sure that it's linked. Okay, so this program is a little different than the other one, but you get the general idea that we do have to set up a certain location where it's going to store the data. So here is my program 6, exercise 6. I am using timeit to measure time or runtime. Then I have to use memory class from joblib. So I would have from joblib import memory. Then I need to remember that we can put this on our drive. So we would create a location. So this variable is going to hold the path, and the path, anytime you work with path for Python, you normally would put it in quotation, single or double quotation mark. So once I set up the path for my storage, I would then now link to it. So creating a storage object called memory, and this is instantiated for memory class. So it is memory class object. And so my parameter would include the path on where it would store. And here you can turn the verbose on, but I put 0 because there's no needed details. So I didn't need additional information there. If you work with servers, you might want to initialize this. Okay. Then we would have the decorator. So before our function, so here we would say memory.cache. And this comes from the actual module. So we set up the cache. Now for the function, we have a Fibonacci function again. And this is recursive. So our base case, which are our seeds, we would say if n is 0, 1, right? So it is 0, 1, then we're just going to return n. Those are the base values. And then we're going to compute the subsequent value after the seed by using a function that calls itself, which is recursive function. So we would take the two prior number, add them together, return, store, retrieve, use it for the call, and so on until we get to the 30th value. Then the last three statement is very similar to all the other ones that you've been seeing in the other program. So when we run this, so you can see that it is slower, right, than what you would see in the a few prior programs compared to dynamic, space optimization. But it is faster than our first program. Okay. So if you simply write a recursive function, then, you know, with and nest in the conditional statement and just run it, it's definitely slower than if you're implementing a storage space for temporary storage. But because the disk is writing as fast, so it depends on your drive, right, or your storage speed, like what it said earlier. And so this is the time that I got. So I would record the slowest, okay, or the highest value time that I got from the output. So after you have the program written, run the program, take a screenshot, put down the slowest time. Then we want to compare this to exercise 1, which is just a recursive function. That's an expensive program compared to the cache and the decorator function, the decorator approach in our algorithm. Is it faster or slower than those? So it's definitely faster than your regular recursion, even though itself is a recursive function, right? But because we had set up the storage space here, it is faster than the traditional program. But compared to the other two form of cache, right? Two form of memoized program, it is not faster. Okay, based on my output from my system. So put down your observation there for C. And then lastly, we want to address these questions. Based on all the exercises, which algorithm is the most efficient? So you can compare your results and you can determine which one is the most efficient. And this is really more on the preference level, right? Even though, and I understand this, I think everybody would prefer a certain way that they're comfortable with. So my job in this lab is to expose you to different ways to do it. And as you learn a certain way, you would prefer how you would solve, right? So when you think about this, you want to also address efficiency. So performance is important in this course. We don't just write program, we want to write good performing program. And that's the objective. Any question? So as we complete that, right, we write up our observation and our conclusion. You don't have to make it really long, just a few sentences will be fine. Okay. And with this, I hope that in the future, when you write your Python program, you can think about how, right, you can improve that program or use an approach that would be given better performance. Any question? Okay. No question. All right. So I'm going to go ahead and stop recording. I'll stick around for questions in case you have some challenges with these lab exercises or other.